Let us proceed with the design example for columns. We have now reached to the sub-question G. You are asked to design the reinforcement for the ground floor column B3, referring to the details given in the questions. Viewing from the ground floor key plane, this is column B3. The orientations and the dimensions of the column is as indicated here. All the beams joining the columns are 150 times 450s. From the first floor key plane, this is column B3. From the elevations, the ground floor column B3 will be this column. These questions assume that the structures is braced, the column is short, and the loops are as given in the figure. Referring to this figure here, the axial loops is 49.12 kN. You have moments at both ends of the column. The upper end has the moment of 13.3 kN-meter, whereas the lower end have 7.5 kN-meter. The cross sections of the columns is indicated here. The moment is acting on the major axis of the section. The specifications is given here. FCK equals to 30 Newton per mm square. The exposure class of the member is XC3. Characteristic yield strength of the steel bar is 500 Newton per mm square. The main reinforcement 12 mm. As for the length, 8 mm diameter. Based on the information given from the question, we know that this is a short column in the brace structures, which is subjected to uniaxial moment, where it is acting in the major axis. Without further ado, let us start with the design process. Given the exposure class, you may start with determining the concrete cover of the column. The nominal cover you may refer to Eurocode sections 4.4.1. You need to get the minimum concrete cover plus the allowance for the deviations in order to get the nominal cover. This minimum cover is governed by three main parameters. First, due to the bar size. Second, due to the environmental considerations. And third, minimum 10 mm. In order for us to get the nominal cover, we will need to start with the minimum cover. Let us find the C mean due to the bar. You may refer to table 4.2. Assuming the reinforcement bar are separated, that means your C mean B shall be equals to the diameter of the bar. In these questions, the diameter of the reinforcement bar is given 12 mm. This leads to C mean B equals to 12 mm. Our next step is to determine the concrete cover due to the exposure conditions. In this case, we assume these parameters are all equals to 0. That gives you these equations, fully governed by C mean durability. To get the C mean durability, you need to refer to table 4.4n. In fact, you have two tables here. Since we are not dealing with the pre-stressing steels, that means table 4.5n is irrelevant in this case. Now we need to determine the C mean durability. It is governed by the structural class as well as the exposure class. The equations tell us that the exposure class is XC3. That means we are referring to this column. Next, we need to determine the structural class. The recommended structural class for a typical design life of 50 years, it will be S4. And then you refer to table 4.3n to see if there is any adjustments in terms of the structural class under different circumstances. Since the question is silent about these conditions, we will assume that there is no adjustment. This leaves us to structural class S4. And the C-mean durability, it shall be equals to 25 mm. Having the C-mean bar and the C-mean durability obtained, C-mean bar is 12, C-mean durability is 25. The larger value of the three, it shall be equals to 25. That gives us C-mean equals to 25. C nominal shall be equals to the C-mean plus the allowance for the deviations. The recommended value for the allowance for the deviations shall be equals to 10 mm. That gives you 25 plus 10 mm. In total, you will need the nominal cover of 35 mm. Next, we need to determine the design moment. We have the absolute already, as given in the question. The moment is also given. However, these are the moments acting onto the columns. We are unable to take this moment directly as the design moment. This is because there may be other factors governing the design moment. Instead of using the moment acquired from the moment directly, we will need to go through a process of determining the MED before substituting into the equations and referring to the column design chart. This is when the classifications of the columns become important. Different classifications will have different calculations for the MED. In this case, we know that it is a short column. Although the questions mentioned to you it is a braced structure, if you see the calculation here, as long as it is a short column, it doesn't matter whether it is braced or unbraced. As for the slender column, the equations to determine the MED shall be influenced by whether the column is braced or unbraced. It doesn't mean that the information given here is redundant. If you observe the previous questions, especially in terms of the calculation step, determining the slenderness of the column, the type of the structure, whether it's braced or unbraced, is important as you need it to determine the effective length. Also, when determining the slenderness limit, whether the structure is braced or unbraced will determine which equations to be used to determine the slenderness limit. Since this question is the extension from the previous sub-questions, we assume that we have done the process of determining the slenderness of the column, and the calculation outcome leads to you a short column. Now that we know the column is a short column, that means the MED shall be governed by the first order moment as represented by the stress diagram here. The MED will be governed either by the M02 or M-mean. M02, it will be determined by the moment acting onto the column plus the moment due to imperfection. The moment due to the imperfection is estimated by using the MED times the eccentricity EI. This eccentricity EI, it will be in the functions of the effective length. that is divided by 400. Since the question here does not provide you the effective length, we may refer to the relevant information from our previous calculations. We refer to the sub-question D here, where the structures is placed. From the calculations, we acquire the effective length. There are two effective lengths obtained, one in the major axis and another one in the minor axis. Since the moment is acting in the major axis, that means we are referring to the effective length of the major axis, which is equals to 2.282 meter. Get the effective length divided by 400, you get the EI. Multiply the axial loops plus the moments acting onto the column, you get M02. You have two moments acting onto the column. We shall use the bigger value for more critical design. This gives us the M02. How about M mean? It is meant for the construction tolerance, calculated on the basis of the axial loops times the E naught. The E naught, it will be in the functions of the dimensions of the column, which is h divided by 30. If you refer to the column section here, you need to decide whether this is the h or this is the h. Now it goes back to the directions of the moment. We have the moment acting on the major axis. That means this shall be the h. Calculate E naught. Multiply with axial loop, you get M mean. From there, you will get the MED. Having this calculations process understood, we shall look into the solution. First, we need to get the larger moments acting onto the column. Two moments here, you get the bigger value, 13.3. Next, we determine the EI. We need this EI for us to determine the imperfections moment, and EI is calculated by using the L0 divided by 400. The effective length was calculated 2.282 meter divided by 400. You get 5.7 mm. Your M2, it will be the M plus NED times EI. NED is given, which is 49.12 kN. This gives you the M02, 13.6 kN meter. Now that we have N02, we will need to get the M mean, which is calculated based on the E naught. The E naught is equals to h divided by 30. The moment rotations is on the major axis. H shall be equals to 300. Divided by 30, you get E naught equals to 10. The equation states that E naught needs to be at least 20. The calculated E naught is less than 20. Therefore, we use E naught equals to 20. Multiply the E naught with the NED, which is 49.12 kN. You have the M mean equals to 0.98 kN meter. Compare the two values. MED, it will be the larger value of the two. Then you know that MED equals to 13.6. Once you have the NED, you're going to adopt them in the column design chart in order to estimate the reinforcement bar areas in the column. You know that there is a series of the design chart with the D per H ratio of 0.05 to 0.25. We will need to use the right chart for us to acquire the as for the column. With that, we need to first calculate the D2. D2 is referring to the distance from the column surface to the center of reinforcement bar. It is calculated by having the concrete cover plus the shelling and plus half of the bar size, as indicated in the equation here. The concrete cover was calculated equals to 35 mm, shelling at mm, bar size 12 mm. That gives you D2 equals to 35 plus 8 plus 12 divided by 2. Your D2 equals to 49 mm. Now you need to get the D2 per H. The H here is referring to the directions of the rotation. It is either this 300 or 150, depending on the directions of the rotation. Since the moment is on the major axis, that means we are referring to 300 as the H. Therefore, D2 per H is calculated as 49 divided by 300 H. That gives you 0.163. Now if you refer to the chart, you have the chart D2 per H equals to 0.15 and D2 equals to 0.2. However, you don't have D2 equals to 0.163. That means you will have to refer to these two charts, get their value, and then do some interpolations. Now let us talk about how to use the chart. You have two axes here. The y-axis, it will be due to the axial load. The equations, axial load divided by BH FCK. The x-axis is determined by the moment. Equations, moment divided by BH squared FCK. You have the axial load 49.12 kN divided by B 150, H 300, FCK 30. That gives you 0.036. As for the M, you use the MED that we have calculated earlier on, not the M1 given in the question. This MED is inclusive of the moment due to imperfections. 13.6 kN meter divided by B 150, H 300 square and FCK 30. That gives you 0.0336. Refers to the chart. We use the chart 0.15 first. The N per BH FCK equals to 0.036. And the S-axis shall be 0.0336. 0.036 is somewhere here. And 0.0336 is somewhere here. The two lines intersect at this point. If you draw a perpendicular line here, the point falls between 0 and 0.1. Let's say we estimate it equals to 0.04. Estimate 0.04 here. And then we refer to the chart equals to 0.2. We will do the same process. 0.036 is somewhere here. 0.0336 is somewhere here. Intercept here. Draw a 90-degree straight line. Estimate the location. Let's say it ends up to be equals to 0.045. That means for these 2 points here, referring to the chart, Different chart give you different results. We are interested with the D2 per H equals to 0.163. And you have the result for 0.15 and 0.20. You may do some interpolations calculations. And then we get the AS FYK divided by BH FCK equals to 0.041. Within the equation here, the only unknown it will be the AS. You have the FYK, you have the dimensions of the column, you have the concrete strength. FYK equals to 500. Column dimensions 300 times 150. FCK equals to 30. Substitute the relevant value here and then solve this equation. Bring the BH FCK to the opposite in the manner of multiplications. Divide with the FYK 500. Then you get the AS. The AS as obtained from the chart shall be the AS required. It is equals to 111 mm square. Provide 4H12. You will have your AS provided 452. How do you get this value? Assuming the rebar is in the circular cross-sectional area, pi r square, the r for 12 mm diameter, it will be 6 mm. Pi r square multiply 4. Why is it 4? For a typical rectangular column, you need at least 4 units of reinforcement bar, 1 at each corner. Why 12 mm? The smaller size of the reinforcement bar shall be equals to 12 mm. This gives you 452, which is larger than the AS required. Now you know that the provided AS is adequate. You will need to also check the minimum bar area using this equation. The AS minimum is governed by the equation, and it should be at least 0.2% of the total cross-sectional area of the column. AS minimum need to fulfill these two requirements. NED given 49 something kilonewton. FYK given 500. AC based on the cross-sectional area of the column, which is 300 times 150. The calculated AS mean is less than the AS provided. That means you have provided sufficient reinforcement bar. Next, you're going to check for the maximum bar area. The requirement is the reinforcement bar area should not exceed 4% of the cross-sectional area, whereas at the lapping length, it should not go beyond 8%, as per the requirement stated in Eurocode clause 9.5.2 bracket 3. What you're going to do here is you take your AS provided 452 divided by the cross-sectional area of the column, which is 150 times 300. This is for the typical cross-sectional area of the column. Now when it comes to the lapping areas, when the same amount of reinforcement bars are being lapped, the total AS provided shall be doubled. That's why this will be 2 times of this. And then check against the maximum limit. The provided amount of reinforcement bar does not exceed the maximum limit. Therefore, it is considered pass. Next, we look at the requirements for the link. We need to determine the minimum bar diameter to be used. There are 2 requirements. The diameter of the shear link, it will be at least 6 mm. and it should be greater than a quarter of the bar diameters provided as the longitudinal reinforcement. The longitudinal reinforcement has a diameter of 12 divided by 4, that equals to 3 mm. You need to provide the bar size at least 6 mm. Therefore, your minimum size for the link shall be 6 mm. Next, we determine the maximum spacing. 4 conditions governing it. 20 times the bar diameter provided. The longitudinal bar diameter is 12 mm. 20 times 12, you get 240. Second requirement, it will be due to the dimensions of the column. The bar spacing should not exceed the B and the H of the column. The B is 150, H is 300. And then the maximum bar spacing shall not exceed 400. Having the 4 conditions here, you get the minimum value. That gives you the maximum spacing governed by the width of the column, which is 150. This gives you the maximum spacing of 150. And then for the H distance above the beam and the H distance below the beam, that means for the columns near the joint with the beam, the maximum spacing will have to be reduced by 40%. Now you will need to get this 150 times 0.6. That gives you 90 mm. Based on the calculated requirements, you propose the shear lengths. Minimum 6 mm, then you provide 6 mm. Maximum spacing 150 for the entire column, then probably you just use 150. Maximum spacing at the joint 90 mm. You can simply provide 90 mm. However, considering the practicality, where the local industry refers the dimensions in inches, while we are designing in SI unit, maybe we just make the dimensions in the intervals of 25 mm. 25 mm is equals to 1 inch. Otherwise, the workers on site will have to do some conversions. To make their work simple, maybe we do it in the 25 mm interval. The maximum spacing shall not be exceeded. That means the proposed spacing here shall be smaller than 90 mm. The closest 25 interval, it will be 75 mm. That gives you the reinforcement. If you refer to the diagram here, you will have 4T12. For the link, you will have R6 150. As for the link near to the joint, it will be R6 75.